We're doing time domain analysis of control systems. I did the first order system, first order prototype system. One concept I forgot to mention there was, these terms, the transient response, which is what happens earlier on before it settles. That's called the transient response, right from time zero on up. The steady state response is what happens as time approaches infinity. So for the first order system, well, here's the transient response, but the steady state response is just a constant one. It's wherever you just take, it's you just let t go to infinity, and that would go to zero, and it would just be one. So it's just a constant one for this prototype first order system. So now let's get to second order systems. Here was the differential equation for the prototype second order system. Zeta is called the damping constant. Omega sub n is called the natural frequency. By definition, it's greater than zero, greater than or equal to zero. We can use Laplace transform to come up with the transfer function, and here is the transfer function of the prototype second order system. And if you remember what we said about the final value theorem, let S be zero, I get omega n squared over omega n squared are 1. That is the final value of the prototype second order system. If that damping constant zeta is negative, you'll get an unstable system, and we don't really cover that because we don't care about the behavior of an unstable system other than it's unstable. I mean, other performance measures don't make any sense when it's unstable. Oh yeah, the final value theorem for unit step, that's when you just plug in S equals 0. It's the simple case. So that is its steady state response to a unit step. Anyway, for the second order prototype system, we have multiple cases. With the first order prototype, there was one parameter it all depended on. Now there's 2 parameters and you get multiple cases. If zeta equals 0, if we just look at impulse responses, we get a pure sinusoid output. As an impulse response. And the frequency of that sinusoid is omega sub n. And that's why it has physical meaning. That's why we call it the frequency, or the natural frequency. Yep, natural frequency. You get eternal oscillation if the damping constant is 0. And think of the mass spring damper system. There's no damper in there. The spring just bounces forever. And note that the poles of the system are right on the imaginary axis. Eternal oscillation, they're purely imaginary poles. The case where zeta equals 1, this is a pure square. So this is what the transfer function becomes. If you take the inverse Laplace transform of that, you get this for the impulse response. And I'll show you a picture of what that looks like next. This is a case of having a real pole on the axis, or poles on the real axis, and it's a double pole, where both poles are at the same place. This is a second order system. We're going to have 2 poles. Here, both poles are at the same place on the real line. The overdamped case is where zeta is greater than 1. So far, we've had it equal to 0, exactly equal to 1, and greater than 1. We'll talk about between 0 and 1 in a second. But if it's greater than 1, we call that overdamped. When it was equal to 1, we called it critically damped. When it's overdamped, you get 2 poles on the real line, but they're still on the real line, right? And this is the impulse response. We'll see what those look like right here. They both look sort of like this. So if you take this system and tap it down with a hammer, and you define down as positive, the response is going to look something like this. It'll go loop up to some maximum value, and then over time get back to where it started. And back. Doesn't bounce. But in the underdamped case, it will bounce. That's when the damping constant is between 0 and 1. You don't have to follow all this, but if this is the transfer function, you can do some algebra, find out where the poles are, and ultimately you get to this thing, which if you look at it, is a sine wave with a certain frequency, which we call the damped frequency, and it has a certain relationship to the natural frequency and the damping constant. And it's in an exponential envelope. And in fact, the poles are located at minus sigma and plus or minus j omega d. So sigma is where it is, how far left. It's the real part, and the omega d is the imaginary part, how far up in the, we'll show you where the poles are. But here's what the response looks like. It's oscillation in a decaying envelope. It's decaying because zeta is positive. So that's the idea. So here's what those impulse responses look like. If the versus pole location. If the poles are strictly on the real line, you just get exponential decay. How far left the poles are tells you how fast it decays. If it's in the right half plane, it's exponential growth. If it's exactly on the imaginary axis, it's just constant. If the poles are complex, then you get oscillation. How far left in the complex plane tells you how fast that envelope decays, and how far up tells you how fast the frequency is. The higher up in the imaginary axis, the higher the frequency. In the right half plane, you get exponential growth. Right exactly on the imaginary axis, you get eternal oscillation. So that's how pole placement dictates or describes the time behavior of a prototype second order system. I think this says everything I just said. If you have complex poles, you're going to get oscillation. If you have no complex poles, no oscillation. Poles in the left half plane, shrinking envelopes. Poles in the right half plane, growing exponential envelopes. Further away from the imaginary axis, the faster the shrinking or the growing. Further away from the real axis, the higher the frequency of that oscillation. And poles exactly on the imaginary axis cause either a constant or eternal oscillation. We'll get into step responses in another video. And we'll be concentrating on the underdamped case pretty much from here out, and I'll tell you why later.